chi of Ox is 1/24th of C1, C2, and I want to write down kx cubed. Right, and here what do I want to write down? Well, let me leave it as a kind of mystery just for the moment. So, we now have, I mean, my work in the 1980s and, lots of other people since then working on Fano threefolds, we know quite a lot of examples. We know quite a lot about threefolds. But still, absolutely nowhere near as much about surfaces. So, how are we going to do n-folds? Well, in threefolds, there was a kind of simplifying trick, which I used already here, which is to say, let's assume the thing is non-singular and canonically polarized. So, people who do differential geometry will assume that the curvature has got some definite sign, or they might call it monotone, or lots of other things they might use. What they mean is that we're dealing with high dimension variety where there are a lot of unknown things, and so we might as well try to give ourselves some easy assumptions so that we can at least start saying something about it. So I want to discuss. So for the rest of the talk, I'm discussing X non-singular n-fold, and I assume that Kx is ample. So in the next talk, I'll be talking about orbifolds, which is one of the things you have to do if you want to go beyond this non-singular assumption. In any case, it's right. And then I'm going to write down, so I'm assuming Kx is ample, and I want to write down the invariance of, I really want to H naught of nkx. Right? And so for curves and surfaces, this is a known formula. We have a completely mechanistic way of writing down the Hilbert series. So let me call this, let me write here sum H naught nkx t to the n. Let me call this px of t. Right? And there's a simplifying assumption that that chi is 1 plus minus 1 to the n times pg. This is not essential, but it just the case that I'm particularly interested in, i.e. hi of ix equals 0 for I. Yes, it's not essential that we have this, but it just adds one slightly more complicated term in the expression. Right, so I call this, so I want to write this Pn. I want to write it Px of t. Right? And the point I want to make is that this function is a rational function satisfying t times px of 1 over t equals minus 1 to the n times p of t. Yeah, and so this is called, this is Serre duality. Symmetry. Or Gorenstein symmetry. Right, so I want to, so minus term in degree 1 if this is not true. Right. So let me come back to this point. Let me look at this p. Let me look at this function p of m equals h naught of mkx. I'm sorry, I'm going to call it PA when A is very large. So this is a standard thing that you do with an ample divisor. An ample divisor says that Serre duality, Serre vanishing says that if you take this A very large, then there's no cohomology except for the H naught, right? And this thing here is called the Hilbert polynomial. So it's not Hilbert function, not the Hilbert series, it's a Hilbert polynomial. So you go up to, when A is very large, this expression here is a polynomial. It's a polynomial given by Riemann-Roch. So the Riemann-Roch formula, this kind of messing around here, the various constant terms here, various properties of the manifold, right? But the expression as a whole is a polynomial in D. Right, and so this expression here is for all A sufficiently large, but this is equal to chi of AKX for all A. Right, and so I'm afraid of cohomology, so I go to some large degree here where all the cohomology vanishes except the H naught, and that allows me to define a polynomial. Having got this polynomial, then I just apply to Riemann-Roch, and Riemann-Roch says that that polynomial is actually the Euler characteristic of this sheaf. Right? So in particular, we know its value also when A is large and negative. So this P of A satisfies P. So if I do P of 1 minus A, so let me say even more basic property. P of A is a polynomial in A with certain coefficients. So the coefficients are rational numbers in general. It takes integer values, and it's minus 1 to the n symmetric under A maps to 1 minus A. Right, and so the 1 that's appearing here is because I chose canonical class x equals O of 1. Right, if the canonical class was some other value, I'd have some other value there, including possibility 0 or 2 or some other number. Yeah? But anyway, this is already lots. Yes? So we know all these polynomials. We know exactly who these guys are. Namely, so let me finish that sentence just a little bit later and just say something that you all know. So if I have these functions, right, then if I take the binomial coefficients A choose M, or maybe it's more elegant to write A plus M choose M, because then they start off with a sensible value, a plus m, choose m. Right? So this guy here is a polynomial of degree m in A, right? And he takes integer coefficients, integer values. Yes? And if I take these polynomials, for all z, for all m, form a z basis for the space of all such. Yes? So I'm not completely sure if this is obvious to you, but really you know it since school days. Right? So if I have P, if P of A is a polynomial and takes integer values, so it's a polynomial of degree n, and takes integer values, then I can do P primed of A, which is P of A minus P of A minus 1. Yes? And what can we say about this guy? Well, this guy is also a polynomial of degree n minus 1, and he takes integer values. Right? And so therefore, by induction, so I told you what the inductive statement is. I want polynomials like this I want this guy here to be a linear combination with integer coefficients of binomial coefficients. So this guy is a combination of binomial coefficients, a Z combination of binomial coefficients. Yeah, up to and including n minus 1. Right, and now I just have to go from knowing this P primed A to PA, all I have to know is one initial value. Right, so I specify who P of 0 is, and then the rest is, and then I'm just adding binomial coefficients. And so, I mean, basically, everybody knows this. Everybody knows it from school, and most of it have taught it to undergraduates over many years. Yes? And so these guys here are, so if I do A plus M, I think it's A plus M minus 1, over 2m. So if you think about this guy, right, then he's certainly a polynomial in A. He certainly takes only integer values, right? And he's plus symmetric. He's symmetric under A goes to 1 minus A. Right? And so, let's just start, let's not be too adventurous. What happens when m is 0, this is polynomial 1. Right? So let's do m equals 1. Right? Now what am I writing down here? I'm writing down A, choose 2. Right? So this is A times A minus 1 over 2. So he is indeed symmetric under A goes to A 1 minus A. So m is 2. This is A plus 1, choose 4. Yeah, and so this is A plus 1 times A minus 1 times A minus 2 over factorial 4. Yeah, and when I do this A goes to 1 minus A trick, it sends A plus 1 into A minus 2, and so it just interchanges the 4 factors. Yeah? And moreover, and these base, and all of these form a Z basis for such. Yes? So in other words, if I've got, for example, a fourfold of general type, then I ask for all of his plurigenera, I want to hold all of his plurigenera in one formula. I say he's got to be a linear combination of three of these terms. Right? And the antisymmetric case is just a tiny little bit more complicated. The antisymmetric case is, I've got it written down, so A plus M 2M plus 1 plus A plus M minus 1 2M plus 1. Right, and so you check again that this one is antisymmetric. Right? So how do I prove of these? How do I prove these assertions? Well, it's very, very easy. It's so proof. So the thing I'm going to do is just pass from a variety to a hyperplane section, right? So what I'm doing is I'm saying pass from P of A, supposed to be of degree n and symmetric under A goes to 1 minus A. Yes, and I just do this same trick. Write down P primed of A to be P of A minus P of A minus 1. Right? Then this guy is antisymmetric under A goes to 2A minus 1, to 2 minus A. And so I just, just go down through, it's just an induction on dimension. And it's, of course, this is a polynomial of smaller degree. So let me skip the proof here and just get to the to something like a statement, something like a theorem. So this is useful because it's motivation for the next lecture. So So define A(n) of T to be equal to. Sorry, I'm going to get seriously technical now. So I'm going to write T to the m plus 1 divided by 1 minus T to the power of 2m plus 1. This is for n equals 2m. And so this thing here is what you get by summing a plus m minus 1 choose 2m times t to the a, summed from a greater than or equal to 0. Yes? And then I need to tell you what it is when n is odd, and it's just slightly more complicated. So this is sum a greater than or equal to 0 of these guys, a plus m, choose 2m plus 1, plus a plus m minus 1, times 2m plus 1, right, times t to the a, right, and this one turns out to be 1 plus t to the t to the m over 1 minus t 2n plus 2. Yeah? And so, I'm just, this thing here is the typical object here, which is anti-symmetric. So these are anti-symmetric under t goes to 1 over t. Right? They satisfy this equation here, which I wrote down earlier. They satisfy this Gorenstein symmetry equation, right, with respect to this functional equation. And this one is the anti-symmetric guy, and this one is the symmetric guy. So, a of minus 2 is 1 minus t. A of minus 1 is 1 plus t. And a naught is t over 1 minus t. And a1 is t plus t squared over 1 minus t all squared. So these things were appearing all over those formulas I wrote down for curves and surfaces earlier. Yeah, and so then the theorem is x an n-fold of general type, kx ample. I'm in characteristic 0 because I'm using Kadara vanishing. So then the plurigenus p x kx of t, so this is the plurigenus, is equal to sum of an integer coefficient beta j times aj, and then plus possibly a single term in degree 1 to deal with the irregularity. Okay, so these bj's here are integers, and they depend only on the first it's n plus 2 over 2 plurigenera. So it's I think I'm going to stop here and let you take a rest. If anybody wants to see these unfinished notes, you're welcome to look at them. So my question here is, if I want to study n-folds, if I'm sort of completely lost any sense of modesty or scale, and decide I want to, because of my success in studying threefolds, I want surfaces and threefolds, I want to study n-folds. The first question is, what numerical invariants I should take? And my answer is these beta I. Right? These are some integers. So they're much better than the Chern numbers. Right, because the Chern numbers, for example, C1 squared and C2. Somebody gives you C1 squared and C2. The first thing you have to do is check that C1 squared plus C2 is divisible by 12. Right? Whereas these numbers here are integers, and they vary freely. There are no implicit congruences among them. Right? So they are given by the first plurigenera, and then they give all the other plurigenera. I should have said this Q is the number over there. It's the difference between PG minus chi plus or minus 1. Yeah. So it's 0 in all the cases I'm interested in. Okay, so this is saying, for example, for a surface of general type, I'm supposed to take k squared, and then times, what did I have? T. Anyway, I think it's to make it. I want to make it symmetric, so I'm going to take it t squared. Right. Every expression every expression I write down is supposed to have this same symmetry. So this guy here is, the top here is degree 4, and the bottom is degree 3, and so this is symmetric of degree 1. Right? And then plus the term involving chi times, and then it'll be t over 1 minus t. And then possibly plus this L1, a minus 2. Right? And that's, so you know, these numbers here, this is the k squared and the chi that are going into the plurigenus formula for surfaces, and you know, they're just appearing here, and these beta I appear in exactly the same way if you want to do non-singular n-folds. Okay, so the great difficulty is that non-singular is not enough. And so that's what the next lecture is about.